Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we have two papers this year at NIPS. One of them was the active learning paper, and the other one is this paper. This one has been kicking around a little bit, but I think there's some nice things in it. So I wanted to go through it carefully. So this is Logarithmic Time Online Prediction. I worked on this with Anna Kormanska when she was visiting as an intern, and Alec was also involved in the project, although not a co-author. Okay, so we're doing multiclass prediction. Doesn't get simpler than that. It's just you have features, you have a label, and we're thinking about this in kind of an online setting. So we're thinking we see features, predict, and we see the truth. And our goal is to just find the classifier, which minimizes the error rate. Very straightforward. And this is the twist. We want this to be fast, right? Yeah. Okay, so why do you want this? Well, if you take a look at the ways classification is often applied, they're often kind of confusing. I mean, often people think about ranking and returning a search result, but really what's going on is you have some sort of index into billions of web pages that pulls up a few which are plausibly relevant, and then you have some sort of re-ranking process that happens over and over again until finally you spit out the final results, right? But in some sense, logically, the problem is really this problem right here. You mean you have to return things fast. You just have 8 billion possibilities, possible labels, right? Or I don't know how many it is these days, but you have many billions of possible labels, which are all of the individual unique web pages. Or another example is here. There's like the who is that question, right? There's almost 10 billion people, right? So that's a big multi-class prediction problem. This one I happen to be able to solve because I know that's my brother and his family. But yeah, otherwise you wouldn't necessarily know. I mean,
does the author write you to use this?
What's that? No, he did not authorize me. I'm probably doing something bad. Okay, so there's a lot of approaches people use to avoid this high multi-class prediction problem. And I wanted to kind of go through those and discuss sort of the obvious things that we're not doing, because I guess we've discovered that a lot of people are used to the obvious ways we're not doing it. So trick number one is when k is small. Often k is small, and that's easy. Trick number two is if you have a pre-existing hierarchy. You just reduce to the k is small case by building a predictor at each node in the hierarchy. And that can work fine if you have a good pre-existing hierarchy. Trick number three is a shared representation. This is very common in ImageNet applications or vision type applications. You have a bunch of shared processing, and then you have a final output layer, right? And because everything is shared here, it's amortized across the elements of the final output. And so you save a lot computationally. And that makes a lot of sense. It's very useful. But it's still the case that you still have that final output layer. And if you have 10 billion classes, things are going to blow up here. There's going to be too many parameters. Okay, so another trick is structured prediction. So the idea here is that you want to make a bunch of individual predictions, and maybe you have some ordering that you impose over the set of predictions that you want to make, or you have some structure of those predictions. So you choose that structure in advance, and then you start thinking about exactly how to do that. So this is very similar to the hierarchy case in some sense, although sometimes the techniques vary a little bit. Okay, so that's a good trick. Sometimes the structure is not very clear. So this is exactly like the hierarchy case in the sense that if you have a good hierarchy, then you can use that, and if you don't, then not so clear. Okay, and then trick number 5 is the GPU. People are hitting things with GPUs a lot, quite hard these days. And GPUs are great, but as far as we can tell, they're only kind of a constant factor grade. So the physics of computation is such that, I mean, maybe GPUs give you a little bit like a constant factor more efficient computation, but it's still only a constant factor more efficient computation than general purpose systems. Yeah, so these are the tricks people like to use. And now let's think about this problem a bit more fundamentally. How fast can we hope to go? And the answer is log k. And you can't really hope to go faster than log k. And the counterexample is very simple. You say, well, suppose my label is uniform on 1 through k. Then, you know, information theory tells me I really have to put out log base 2 of k bits in order to be able to even specify a label. And so there you go, log k time, right? It's kind of the end of the story. You can't really hope to go faster than log k. And then if you look at the way things work, right now, typically order k is what you see. The amount of computation that goes on to predict one of k things is order k. So, okay, so k divided by log k. What does this mean? So when k is kind of small, it doesn't really matter very much. When k is 100, you might be like, okay, well, I mean, a factor of 10, I guess maybe a factor of 10 was important, but it's not too important. If you get up to 1,000, then, you know, looking at a factor of 100 or so, maybe it starts to become important. But, you know, GPUs are really good at doing a bunch of parallel computations, so maybe even a factor of 1,000 is not, or a factor of 100 is not so important because you can just crush this with a GPU. But when you get to 1,000,000 here, you're looking at a factor of 100,000 or so, well, I think even if you have a GPU, you're going to start to care. Okay, so the claim is that there is some k for which you care to be sublinear in k. And in particular, it would be nice to be logarithmic in k. So now the question is, how do we actually get there? So there's a lot of approaches people have taken, including myself. I worked on this. So for sparse encrypting output codes, what happens is you say, I'm going to create some binary vectors with a length of the number of labels. So it's a bunch of 0, 1 entries. And then I'm going to train some binary classifiers to minimize the error rate. So I want to predict that bit, essentially, right? So I have I have log k different, or order log k different binary classifiers, each of which predicts the bit in my binary vector. And then I want to predict by finding the y with minimal error. So if the value of biy is 1, then you really want the h sub I of x to equal 1, or 0, or vice versa. Okay, you guys can figure it out.
What is a vector index? Is it a binary vector? Is biy a vector? Itself is a vector?
Yeah, so what I mean is there's really a matrix where one dimension has size order log k, and the other dimension has a size order k. Right? And biy is the ith entry of that matrix. But each predictor is only trying to minimize the error rate on one dimension of that matrix. Right? So this is only an HIX.
That should be by maybe?
You
create log k binary vectors. Each one is b sub y. biy is...
biy are the entries.
So these are the entries. Think of them as the entries.
Yeah, b sub y. No, like
Yeah,
the way it's written. Like
b
b sub y.
Yeah, you're confusing the entries with the
So
vector.
b sub y is the vector.
Yeah.
Man. Okay, so here's my fundamental flaw. I took general relativity, and I do Einstein summation notation, and so I always notate things. I talk about the entry and define its indices. So think of it, this is a scalar, which is the I-th entry in the matrix, right? And then the whole transpose thing people do, that really confuses me.
And then your background limits you, but you can be able to shake it off.
I'm trying, but I don't quite understand.
Because you don't have log-concave those, you have k-log.
We're not doing general relativity at all.
Yeah, I don't understand why it's unclear, I guess.
It's clear. No, what you're talking about. That's clear.
Maybe we should discuss later. It seems like a distraction. Okay, so the question is, why is this not logarithmic time?
Length k vectors, how are you going to read?
Say again?
You have this length k vectors, so you want to read these unit k?
Yeah, so the length k vectors, actually, I think that's not really a problem because we kind of imagine that we have at least one example of each label. All right, so we can kind of amortize the length of the vector across the individual labels.
Or you want it per label?
Yeah, we want to do logarithmic time prediction per example.
You even don't have to really create them. So if you imagine the label is just even a number,
Yeah.
so the vector could be just the ith digit in the binary extension of this number.
Could be. But I would still say this is not logarithmic time.
Step 3.
Yeah. Step 3. So when you find the y with minimal error, that's typically an order k operation.
If you have 0 error, then not, right? So let's look up table. It's all 1.
Your lookup table, that could be true. This is order log k. There's a constant which is larger than 1 here. So the lookup table is not size k in that case. It's going to be size kind of large.
But John, doesn't that depend on how sparse the
What's
the
your
first
step
step is?
3? I'm confused.
If the first step creates a very dense matrix, any prediction produced in step 2 can be done in constant time to solve step 3. Just a reverse lookup.
So say it again.
So if, let's say in step 1 you create very dense, not sparse, but dense.
So B is dense.
dense.
Yeah.
Then whatever you produce in step 2, it's just a binary representation of one of the k labels.
That's
and then
right.
in step 3 is just a constant time.
Why is it constant time?
Because we don't need to, there's no, the one that is produced in step 2 gives you a minimum error of 0 in step 3. It's dense.
That's the same thing that I was saying. So if you have no error in step 2, then step 3 is constant.
If you have no error. I'm
And
a little bit worried about errors.
Yeah, if you're a little bit sparse, you can, let's say you can guarantee that in step 1, every true label, a miscible label, can find a vector in step 1 with edge distance of 1 or 2, small edge distance. Then in step 3, can you just do some local search to get it? It's still okay.
Maybe. So this particular paper didn't do that, but I'm not saying there isn't an approach along these lines, but the paper certainly didn't do that. The paper was just saying, look, we're going to check all the individual labels.
So 3 is kind of like, is it like some kind of a nearest neighbor problem?
Yeah,
So
essentially.
why should that be linear? That seems to be a really horrible way to be solving these neighbors.
Well, we do error correcting in communication, right? It's
Yeah.
not linear.
Okay, so
I
go
mean,
for it.
There's other problems that I see with this, but not the step 3. Like to me, it seems to be the issue of that the problems that you create can be substantially more difficult
Yeah.
than the original problem. Like that's what I think is a worse problem here. Because 3 you can just solve with the right data structure, I think.
I'm less convinced of that. Ben, I think these two problems are related. So when you have a particular problem and a representation that you're worrying about, you really want to be tuning the bits here to match the problem representation that you care about, which means that it's not going to be the problem representation which happens to give you logarithmic time. I mean, you can. I mean,
But I think this is the problem. The problem is not computing that, because if you didn't have this problem that some combinations, some selection of bits are hard, then use turbo code, use all this fun stuff, and it's not linear, right? You can solve it. The problem is that the problem that you generate, the B vectors, are such that you're just going to get horrible results.
Yeah, I think that's
okay. Yeah. So prediction is omega k. I think. Okay. So let me rephrase this in a way which may be as palatable. I think the prediction is omega k if you're tuning the B's to match your representations. Because then you don't have a turbo code anymore.
I believe it's true, but that requires it.
Okay, so another approach people use, step 1, you build a confusion matrix of errors. And then step 2, you recursively partition to create a hierarchy. Maybe you use some sort of spectral method or something to partition things. Approach 3 is you have a hierarchy now and you just use it. So you use your hierarchy solution. And I would say this is not what we want either. So why is that?
Accumulate errors.
What's that?
You accumulate errors.
You have cumulative errors going down. That's true, but I mean,
Step 1.
That's worrisome. Yeah. So it's step 1, I think, which is the really killer one. So if we go back and we think about this graph, you can afford to spend more time on training than on testing, maybe out to 10,000 labels or something. But beyond that, you really need to have, I mean, having something which is logarithmic time in training also matters.
But by this, you mean logarithmic overhead compared with the size of the data set, right?
I'm thinking about logarithmic time per sample, per example.
For example, yeah. So
this doesn't seem so convincing. And then there's another trick here, which is pretty cool. This is unnormalized learning. So this is a simple one against all approach. You have a predictor for each class label, and you can just build a predictor, is it this class label or not, right? So the one against all, it's order k. But there's a trick, you can actually make the training very fast. You can say, we're going to train, for this example, we're going to train the y-th regressor with x1, and then we're going to pick a random other regressor and train it with -1. Okay, and now the training has become essentially, I mean, just for every example, we just do 2 updates, so it's essentially constant or logarithmic or something like that. So that's fine, but the prediction is still going to be omega k. So this approach is actually kind of effective. It's good for training, but not for prediction. Okay, so now we want to think about how do we actually do this? And we're going to think about learning a tree, which has a problem with accumulating errors, but we have to start somewhere. We need to think about how do we actually want to do things. So let's imagine we're doing digit recognition, and we have 1 and 7 and 3 and 8. We could do a split at the root between 1 and 7 and 3 and 8, and then we could have a hard split further down between 1 and 7 and then between 3 and 8. Or we could have a hard split at the root between 1 and 8 versus 3 and 7, and then have an easy split further down. So now the question is, do you prefer having the hard split at the root, or do you prefer having the hard split further down? Any opinions? You think you prefer this one? So we preferred this one. Okay, so the claim is that it's better to have confusing problems near the leaves, or difficult problems near the leaves. And the problem is that, so you have some representation which is being used at the root, and that representation is getting hit by all the samples. So it becomes very constrained in the sense that it needs to get a lot of things right, while further down near the leaves, you you get fewer samples, you get fewer things right.
But that's the thing, precisely because first time you get the less samples, you want the easy to classify. When you have more samples, you hope you can deal with the confusion better. That's my reason.
So I think Lin is making a statistical point, whereas you're making more of an optimization, like an expressivity point.
Yeah, so I'm making a point about representational capacity. Because I think often the representational capacity ends up constraining your performance. The representational capacity, or rather, I think the way it works is representational capacity constrains your performance at the root. Sample complexity constrains your performance towards the leaves. Yeah?
Who is BWG?
Bengio, Weston, Granger.
So there is another point, which is for a lot of these algorithms, if you make a mistake at the root, then you have no way of recovering from it often. So just mistakes at the root are more costly, and so you might want to put easier problems there.
You can recover, in this because you can recover from mistake at the leaf as well. So
we will actually have some ability to recover from mistakes because we'll have the same label may be in multiple leaves. Okay, so we need to think about what is a good partition of into some right and left branch. And this is easy when you only have two classes, but it's actually fairly subtle when you have many classes because it's kind of very fundamentally non-convex. So we have a bunch of examples, and we want to look at the quality of some partitioner. So we want some way to judge how good different partitioners are. And the claim here is that a decent way to do this is to, okay, so if the probability of A times the probability of B was equal to the probability of AB, then it would be as if these were independent. Right? As if A and B were independent. But instead what's happened here is we're trying to maximize that difference. So we're trying to maximize the dependence between the left-right decision and the label. Okay, so that should at least intuitively be something along the lines of what you want.
So this is like a purity criterion of sorts, or?
It's not just a purity criterion, because you also want the number of examples to be going, a similar number of examples to be going left as right. And so we're weighting this by the fraction of examples and not just by the some uniform distribution over classes.
So isn't it something like the Pearson correlation coefficient? So you want the Pearson correlation coefficient to be large?
Purity usually weights, no? By number of examples.
The Pearson correlation coefficient between the H and Y, right? This is what.
Could be. I don't know Pearson correlation coefficient offhand. So in the paper, there's a property called purity and a property called balance. And you kind of want both of them in order to, and this achieves both of them. Or at least it drives you towards both of them.
Because I'm thinking about the kind of typical the purity measure or impurity when you're just kind of just growing decision trees, right?
Yeah.
So that one usually weights by the sizes. It's not purely just how good your conditional distribution looks like.
Yeah. So if you look at a typical entropy-like thing, what you see often in decision trees, it looks kind of like this. I wish I could draw better, but okay. And then what we're doing looks a little bit different. It looks kind of like this.
Right. Okay.
Right. So it's a bit sharper. Since we're trying to maximize things, this is somehow a bit less non-convex than that, which makes it a bit easier to optimize later. Okay, so there's a different form of this, which I think is a bit more operational. You can factor out the distribution on Y. And now you can kind of see, you're looking at the fraction of time that you go right, and then the fraction of time that you go right condition on the label. Right, so those are kind of the fundamental quantities that you're trying to work with. Okay, and then now you can see why this is sort of non-convex, because so when you're doing classification, if you take all of your labels and you swap them, you get something terrible performance-wise. But if we take our partition and we swap it, we get something with the same value here, right? And now, if you take an average of those two, you get something terrible, because the average of a good partition and the complement partition is going to be predicting. Well, the question is, what do you do with a tie? But nothing good can happen if everything is a tie. Okay, so that's it's kind of rough. I mean, we're used to convex optimization. Convex optimization is much easier, but this seems kind of hard. Okay, so now we need to think about how do we. So we don't just need to optimize this criteria in an individual node. We need to optimize it in many nodes across the entire structure. And one question is, can we build things in a bottom-up fashion? It's kind of a natural approach you might imagine. You take two random labels, you build a predictor between the two, you combine with other subtrees to make a supertree, and you build up some sort of tree-like structure. And the claim is that this does not work very well. And this counterexample is here. So you have three labels on a line, single feature, which is the line. You're doing linear prediction. You pair 1 and 3. You build a great predictor between 1 and 3. And then you pair that with 2, and there's no linear predictor which can distinguish between 2 and 1 or 3. So some sort of randomized matching and then build up to get the big structure approach seems to not be viable in general. At least we haven't been able to figure out a way to do it. So now the question is, can we do things in a top-down fashion, right? And it turns out you can take, there's this notion of decision tree learning as boosting, which people have worked on previously, and you can take these, this proof and you can redo it for the multi-class case. And what you end up with is, so we imagine that we make some progress on our criteria, gamma, just like a boosting assumption. And then you can prove that the number of nodes in your structure is something like this. And the gamma also causes you to get a log k like depth. Okay, so this is something nice. It says that if we optimize this criteria effectively at every individual node, then we can eventually hope to get a small error rate.
So is the basic idea that you reduce entropy at each step, so at the bottom you must have like pure leaves?
Yeah, so inside of the proof it's doing that. That's right. It also says something a little bit distressing. It says that if gamma is small, that's in the exponent, that's bad. So we can't really afford to have a small gamma. You need to be doing strong learning, not weak learning in the individual nodes. So we really want to strong learn the predictors in the nodes of the tree. Otherwise, it's just going to the tree is going to be enormously large. Okay, so now the question is, how do we actually get a good gamma here, a big gamma, at the nodes of the individual tree? And there's a couple common tricks that we use. The first one is you can relax the optimization criteria. This is kind of a heuristic. We relax optimization criteria to use some sort of score margin-like thing, rather than using the hard decision left-right. Right? So if we go back here we're looking at just did we go left or did we go right? Here we're looking at the expected score on like a -1 to +1 range, and then everything is the same. But even this is kind of hard to optimize, because every time you change the parameters in your y hat, you'd have to recalculate this to get the exact value over all of your examples. And that doesn't work very well, so we approximate this with a running average. Right, so you have some running average of what this value is, some running average of what these values are, one for each y, and then as your learning rate converges towards 0, the running average should converge to the expectation. Okay, so the algorithm at the node then looks something like this. You start with your running averages are 0 for each of these. You compare EY to E. So this is the expectation conditioned on Y. This is the Y independent expectation. You create a label, which is +1 or -1. And then you update the weight just using that binary label. So we're using an online learning algorithm, online classifier underneath, right? And then you update your statistics to just keep everything up to date. Okay, so this is kind of the core update rule that you apply at an individual node. And then of course, you're going to go left or go right, depending upon what your update says. And then you're just going to recurse doing this at all the nodes in your structure. Yeah?
So y hat of x is just W transpose times x?
Yeah, so we're using linear predictors in our experiments. But anything that, I mean, it should work with any online classifier outputting a score that you can use up there. Okay, so now the question is sort of what happens experimentally. There's many different experiments you can do. One experiment is, let's say we have a fixed amount of time, and we just reduce data sets so that the amount of time used by individual algorithms is the same. Right, so we can compare this logarithmic online multiclass tree to 1 against all, looking at the accuracy, so higher is better, for a bunch of different data sets that we found. And what you see is, okay, so for this one, I think the 1 against all is slightly better, and then it just gets worse and worse and worse and worse as you get to more and more classes. So the LOM tree, on a per computational time basis, the LOM tree is getting at accuracy much better than an order K approach.
Hey John, about this,
Yeah?
there's one correct label.
Yeah,
There's always just one correct label,
yeah,
and everything else is
wrong.
equally bad.
Yeah.
Okay.
So this is the 22K version of ImageNet. So that's like the big version of ImageNet. This is a document hierarchy that we got from Paul Bennett.
I mean, one could argue that if you have a hierarchy, you should measure your error proportional to the graph distance in the hierarchy or something.
You could argue that. It's not what we're trying to do. We're trying to see how good this is at just flat out, straight up doing high multi-class learning.
But is there a way to kind of, if you had a hierarchy and you want to use a method there, is there some way to inject the hierarchy into your method?
I mean, there's no interface for that right now.
Not in terms of
I could certainly
interface, but in terms
imagine biasing the training process to obey a hierarchy to some extent. So, I mean, right now, this is really just an online procedure which is going on inside of. So the order of examples really matters.
So
if you had some pre-existing hierarchy, then maybe you could make it so the order of examples doesn't matter so much, right?
So John, like, is there a way to view this as some kind of a stochastic subgradient descent or something like that? I'm just trying to understand. I mean, like, is there any high-level intuition for these 5 steps?
It's really just these 2 steps.
I see.
These are just statistics. This is just
Oh,
counting.
I see. So these are just some kind of sufficient statistics, but
Yeah.
I see. So just really, I see. Oh, so then b minus 1 and 1, that feels like subgradient of a. So you are doing subgradient descent on the absolute loss. Okay,
That's right.
Okay.
So
Yeah.
we have this loss structure, so it's plus or minus 1.
So I guess in that case, is there a way how to then incorporate hierarchy through what I guess Offer was suggesting? So rather than having 0, 1 error, you might have some kind of version of the nearest common ancestor type error, right?
Yeah.
And there might be a way how to write it again, like some kind of piecewise linear function, so you'd be able to do some kind of other gradient.
I think that's plausible. We haven't done it, but I think it's plausible.
So in some sense, your measure of purity, right, would then be not treating all the classes equal. Like that would be the way to modify it, right?
Yeah.
So, but instead you would be incorporating into the measure of purity.
Yeah. So another thing to think about at the moment is just okay. So you can see where this optimization kind of fairly directly implies +1, -1, something just classification. If you have this kind of thing that you care about, it's a bit less obvious exactly how you would want to do it. There are, since we started this, we have found some other approaches for optimizing linear predictors under this kind of criteria, but they involve things like you kind of create a sigmoid, so you pretend that there's some fraction of the time that you go left and some fraction of the time that you go right, and that kind of continuizes the optimization. Then you have to worry about regularization maybe a little bit harder and so forth. Okay, so actually for fixed training time, and then we can look at, okay, so this is test error, so lower is better now. We can look at the test error for a bunch of other logarithmic time approaches. You can have a random tree, you can use a filter tree. This is an earlier paper that I worked on. It's also a logarithmic time. It's not learning the structure, it's just but it is something nice there. Okay, so we see that generally the test error is smaller, sometimes it's much smaller, depending upon the degree of compatibility between the representation and the problems.
So what hierarchy do you use for filter tree?
It's just the bit representation of the label. Okay, so
can you say and random is what?
it's just a randomly created hierarchy, basically. So you create a random hierarchy.
But without filter tree, just training top down.
Just training top down in the way you normally would, right? So the filter tree is a technique which is, so if you train top down, is it this subset or that subset? It's a problem because it's actually an inconsistent training algorithm. Filter tree fixes that, and essentially it trains bottom up in order to, on a fixed hierarchy, yeah. Right, so filter tree is better than random tree, and then this LOM tree seems to be as good as, or better, and sometimes much better than the other trees. Okay, so now we can also run one against all, at least on some of the smaller data sets. This is just, we don't care about computation, we're just going to try to optimize to get the best prediction performance we can, right? And what we see is there's still some gap, right? So that's disappointing, but it seems like it's where we are right now. We've closed the gap statistically to be much closer to one against all than we were previously with logarithmic time prediction, but I don't think that it's at the case. It's not the case yet that you just want to use this no matter what. You need to care about the computation if you would prefer to use this. Okay, and the last question you might ask is, do we actually get logarithmic time in prediction? And the answer is yes, we do. So the reason why this question is non-trivial is because when you have these branching structures, they're not nearly as cache local and highly optimized as BLAS operations or whatever, right? So you expect to pay some penalty associated with the fact that you're branching, and that there is a penalty if you look at this, but indeed it's still generally logarithmic time, right? One of these numbers may be, so let me go back to, so this ImageNet here is, Leon Batu trained a convolutional neural network, script up to the top layer, and then use that to create feature vectors for all of the examples in the 22K version of ImageNet. And now the prediction here takes half a millisecond on the CPU. So it's decent. Yeah?
Do you have a sense of where Manek's approach would sit on that graph?
Yeah, so I think, so Manek's approach is going to be slower. So we haven't done side-by-side comparisons. I've tried to understand the performance characteristics of the fastXML. I think it's roughly a factor of 10 more state and factor of 10 slower than this approach on the data sets that he was applying things to. But the performance, I think, is better than what we're getting. Right? So
it should be around the same as OAA performance-wise, right? Statistically, most of the cases. Or
I guess I'm not entirely. I expect it would perform better. I don't know if it completely closes the gap.
Perform better in terms of accuracy and but slower in terms of time.
What's that?
So you say it's going to have better accuracy but slower.
It's better accuracy but slower and more state.
So what is its so you have what is its complexity?
FastXML?
Yeah.
It's not analyzed, but it's okay. So Manek is not using online learning. He's using some sort of iterative optimization, and the number of iterations is not very controlled. But in practice, it's relatively small.
At prediction time, for example. Like
it's going to be it's logarithmic time for each individual tree, but then there's a bunch of tree, and he's doing bagging-like things or random forest-like things. So it's dependent upon how many individual trees he uses.
I see. So there is, and that will, and then there is no. Is there any intuition for like how the number of trees that you need will scale with the number of classes, or is this something that's just one of those things that depends on more on the problem than on the number of classes, or?
Probably asking.
Yeah,
I think Manek is the person to ask about that.
Okay.
Yeah. Okay, so can we predict in time logarithmic and K? So
There's a recent ResNet talk. He was here just the other month and gave that talk. So just look it up.
yeah.
You guys know about it. So what's the answer?
So there's right now the LOM tree does not incorporate the benefits of the filter tree. So when you have a high noise rate, it's good to have a training rule which is consistent, and that's what you encounter with multi-class prediction. So maybe there's a way to fix that. As soon as I get a moment, I'm going to try some things, and I think we do know how to do that now. And then there's also this issue that you have your representation complexity constrained at the root, your sample complexity constrained at the leaves, and it's kind of it's something that's fundamentally uncomfortable about a decision tree. And so maybe there's some other approach which is less decision tree-like that also gives you logarithmic time. Are there questions? Okay. Yeah?
So when if the problem, distribution or label changes over time, then do you have to retrain everything from scratch?
No. So this is an online approach, and there's actually a bit more to making things online that I didn't describe. So you can have nodes that become obsolete because all examples go away from them, right? And there's some process of recycling nodes in an online fashion, which is described inside the paper. So when the distribution is changing and you want logarithmic time, I think that there is no good alternative for this. At least I'm aware of nothing else that possibly works. Okay, thanks a lot.
Okay, so now we're going to be Bayesian. And instead of minimizing a convex loss, what we want is to sample from a distribution which is derived from this loss. So I will tell you exactly what I mean. And what we will see is that the algorithms that we know and love to minimize a convex function can also be used to sample from the measure derived from this loss. Okay. So as always for the past year, my story starts with a convex body in Rn. So K is a convex body. So it's a convex set, compact, with non-empty interior. And what we will have is a function f, which is going to be from K to R, which is convex. Okay, so we have a convex function defined on our convex body, and I'm going to assume that this function is smooth in the sense that it's L Lipschitz. Okay, so the gradient, the norm of the gradient is bounded, and it's beta smooth. Okay, so the gradient map itself is Lipschitz. Okay, so the gradient of f of x minus the gradient of f of y is in Euclidean norm. This is the Euclidean norm is less than beta norm of x minus y. Okay, and the object we're going to be interested in is a log-concave measure, which is derived from f. So mu is going to be a probability on k. And I'm going to write for you the Radon-Nikodym derivative of mu with respect to the Lebesgue measure, or just the density, sorry, of mu. So the density of mu with respect to the Lebesgue measure, d mu over dx, is going to be equal to 1 over z exponential minus f of x, indicator that x is in k. Okay, and z is just a normalization constant to make this a probability measure. So z is equal to the integral of exponential minus f of x dx over x in k. And the problem we're going to be interested in, the goal, is to sample from mu. Sample from mu given some oracle access to mu and k. Okay, so that's going to be our problem. So, for instance, this morning, Ofer talked about decision trees and how to optimize the weight on the decision trees. So what he was interested in is minimizing f over those weights, but now we're taking this Bayesian approach where every weight has a certain probability. And then you might be interested in doing different kinds of inference using the distribution itself. Okay, so this is a basic task. And the constraint k, for instance, in Ofer's talk, it was about, he had this proper and valid weighting of a tree. So this gives you a polytope for k. Okay, so this directly appears in real life example. So this problem has a long history. I'm going to tell you about this in a minute, but first let me tell you the result and the theorem that we proved. So this is, by the way, the paper that I have at NIPS with Ronan Eldan and Joseph Leac. So the algorithm is the simplest you can think of in some sense. So what we will have is xi1, xi2, etc. An IID sequence of Gaussians and zero identity. And we will have eta positive step size. And what we're going to do is the following. So we are going to start our initial point, x0 is going to be 0, and I'm going to define my sequence to be x tilde. There will be another sequence which is more deserving of the name x, okay, so x tilde is this. So x tilde k plus 1 is going to be the following, so I'm at x tilde k. What do I do? So, okay, so the points where f is small, they have a higher probability. Okay, so I want to drift towards the minimum of f. So to do this, I know how to do it. I just do a gradient step using the gradient of f. So I do minus eta gradient of f at x tilde k. If I do that, I will go to the minimum, and I want to keep some variability. Okay, so what I'm going to do is that I'm just going to add one of those Gaussian. I'm going to add some noise. So plus square root eta psi k. Okay, this is, so it's very much related to stochastic gradient descent. Okay, this in expectation is just equal to the gradient. Okay, the catch is that the variance of my noise is exactly equal to the step size. Okay, so the usual theorem telling us that stochastic gradient descent will go to the minimum do not apply, exactly because I'm in the regime where the variance is matched with the step size, and I should put eta over 2. And the theorem is very simple. So it's myself, Ronan Eldan, and Joseph Leac. So let's do, so we need some kind of normalization somewhere, right? Because, I mean, K was just an arbitrary convex body. So what I'm going to assume is that K contains a unit ball. Let's say the diameter of K, I denote it by R. And to simplify, we're going to assume that L and beta are some constant, numerical constant. Okay, we can, I mean, the theorem, it has all the parameters in the paper. Now the theorem reads as follows. the total variation distance, so you remember the TV between nu and mu is just the supremum over all events of the difference between the probabilities that nu assigns to A minus the probability that mu assigns to A. Okay, so if I control this, I control uniformly over all events the different probabilities. So it's a very strong notion of convergence. So we're going to say that the total variation distance between x tilde n, after doing capital N step, and mu is less than epsilon if I set eta to be some, let's say, a constant times r squared over n, r squared over n. Okay, so that's what we prescribe for the step size, r squared over n. And the most important thing is what is n, capital N. Capital N should be at least, it should be at least, so square root r times n over epsilon. So this looks pretty good, except that it's to the 12. Okay. so that looks less good. But the point, the point is that it's polynomial in n, right? So what is the difficulty of this problem? Let's focus. Yes. Yeah, of course. Please.
So mu is a measure.
Mu is a measure. Yes.
Then x twiddle sub n.
Yes. This is a point. Yes, in Rn.
So what's the total variation between?
Oh, yes.
X and
so first of all, I forgot two things. So one of them is So here I identify the random variable with its measure. Okay, so this is a random variable. It has an underlying law, and I identify the two. But more importantly, I forgot the most important thing, which is just like in stochastic gradient descent, when you do a step of gradient descent, you might step outside of your constraint. So you need to project back. Okay, so you project back, and this will be actually the whole difficulty. So where pk is the Euclidean projection. Euclidean projection on K. Okay, so if I step outside, I project back on K. Okay? So then I get indeed a point in K, and I say that the total variation distance is less than epsilon, provided that I get this. And if L is 0, meaning that I'm really interested in the uniform measure on this, then we can improve it a little bit. Then 12 becomes 7. Okay, so at least that. Okay, so let me tell you some of the history of this problem. Not much, but a little bit.
Sorry, what do you mean by L0?
Sorry? L is 0 just means f is constant. So I want to sample a uniform point in K. Okay, so the first one to do this, to prove that there exists a polytime algorithm to sample from this type of measure was Dyer, Fries, and Canaan in 91, I think. And what they did is essentially this thing, okay, exactly this. So they were interested in the case where f was a constant, so there is no gradient. But the point is, instead of the projection, what they were doing is, if you step outside, then you just repeat. Okay, you don't move, and you repeat. So the thing is that this type of Markov chain is called a ball walk. This will not mix from any point. If you start in a corner, then you can get stuck, and it can take exponential time to make a move. You see, if you are in a corner like this, and I'm here, and I have my small ball, most of the time I'm going to step outside. It's going to take a very, very long time for me to start moving. And what they proved is that from a good starting point, you will mix in polynomial time. Whereas what we do mixes from anywhere. I didn't say anything about where you start. And why do you mix from anywhere? Because even if I start here, you will see the picture I'm going to draw will make sense in 20 minutes, is that I will move like this. I will escape like this, okay? I will keep bouncing on the boundary, and this will make me escape very fast. Okay, so that was, the first one was Dyer, Fries, and Canaan. I think they got, now I don't remember, but something like n to the 21. And the current record is by Lovaas and Vempala. And they get an amazing n to the 4. okay, using what is called the hit and run. So hit and run is the following. It's very simple. You are at a point xk, and now xk plus 1 is going to be sampled from a certain distribution, which is the following. So I first take L at random from the sphere, okay, so uniform on the sphere. So I take a uniform direction, and then I sample xk plus 1 from mu, restricted to the line induced by L starting at the point xk. So I was here, that's my xk. I take a random line, okay, and I take a point uniformly, not uniformly at random, but at random from the restriction of mu to this line. So sample from mu restricted to the line xk plus RL, or LR. Okay, so this is called hit and run. This is a one-dimensional problem, and you can solve it in many ways. The point is that these two algorithms are very different. So, okay, they get a better dependency than us, definitely. This is a zeroth order method. What it needs is to be able to query f at a point, okay, to query the value of f. What we have is a first order method. Okay, you can query the gradient of f. So what I expect, or what I hope, is that this type of method should be better in practice. You know, it's using much more information about the function, so it should mix faster. It's not yet shown in the theorem, but that's what I hope to obtain. I will tell you towards the end about real experiment. So that's one thing. This hit and run also mixes from any starting point. Yes?
If I remember correctly, the work of Logarithmic Time Online, they had to go through a succession of convex bodies. You don't just start with an arbitrary body.
So that's if you want to compute the volume.
Oh, so for the sampling, they didn't have to do it?
So here for sampling, this works directly. And they proved, so I mean, you know, there are many papers, but one of the most recent one, which is still, I think, I don't know, 7 years old, shows that it mixes from any starting point. So you don't need a warm start or anything like that, which is just like what we do. So one thing which is tricky is that, yes, we are fighting with them, and they worked a lot on this, so this is very optimized. But still, I expect, I mean, okay, our point was to prove polynomial, and let me say something else which is disappointing, is that this is n to the 4 times log 1 over epsilon. Whereas we get polynomial in epsilon, and this is a key difference, and yes?
So let's kind of not worry so much about algorithm for a moment.
Okay.
Okay.
Yes.
So suppose I can solve the minimization problem over the set. Right?
Yes.
So do you expect I can do a better algorithm if I just do a series of full minimization problems of perturbed functions?
No, I don't know. I don't think so, but I don't know. So it's a good question, but here you will see, I mean, what is underlying this is a certain diffusion process, which has mu as its stationary measure, and so it's very natural to just discretize this diffusion process. And it leads to gradient descent, but you know, it's in that way that you do it. You start with the continuous thing, you discretize, and you get this. And then you see that there is a connection with optimization. But maybe there are other ways to do it, but yeah.
But probably in that process you're doing sort of a Taylor approximation somewhere, which leads you to the derivative or not? So
you will see. It's a bit subtle because, you know, you're working with those random variables and you need to couple them, in fact.
Right.
So you will see. We're going to do that. I guess one other thing. Yes.
So just to make sure,
yes.
I mean, your main selling point is that you think this one does better.
My main selling point is that this is a natural algorithm that you may want to use, and that is actually used a lot. So this is called the Langevin Monte Carlo, actually, I should say. This is Langevin Monte Carlo, going back a long time. And it has been analyzed without the projection. So that's what's going to be my next point. So in statistics, people really look at this, and it's known how to analyze it when you don't project. But the projection induces a lot of real difficulties, and we have a way to deal with them, and which, you know, can give you, in a broader context, new insight about how to deal with those projections, because this is something you really deal with quite often.
If you don't project, then what happens if you step out of K? You just ignore that step, or?
If you don't do the projection?
Yeah, you just ignore.
Yeah, that's what Dyer, Fries, and Cannon did. Yeah, you just say, okay, I don't move. I try it again. And you count the number of failure. And so this will not be polytime from any starting point. So, okay, so Dalalian in 14, analysis of LMC for k equals Rn and F alpha strongly convex. Okay, so our starting point was this very nice paper of Arnac-Dalalian, who showed how to analyze this in the case where the potential has some curvature and there is no constraint. Okay, and I'm going to walk you through this. It's very nice, very simple, and then you will see what are the difficulties and how we deal with them. Maybe just one last thing that I wanted to say about this. Here you see you're playing with the boundary at every step. You know, every step you have to go and see how far can I go in this direction. Whereas what will happen with this guy is that most of the time you don't have to play with the boundary. It's only from time to time that you step outside, you project, and then you wander again inside, and then you project at some point. So there is some notion of average complexity, which should be lower for this algorithm than for the hit and run. But this we didn't do. Okay, but in practice you see it. I mean, this you just have to do it every time and not there. Yes?
What you just said has to do with, I mean, you're assuming that the minimum of the function is somewhere deep in the interior of the convex body. If it's on the boundary, then you are...
That's a good point. So, I mean, yes, it's almost a good point. So, the thing is... no, but, okay. No, let me explain. So you will see, I will make this precise. We will exactly need this. But the point is that for any f, which is smooth enough, there is not too much mass near the boundary, actually. Okay, so near the bound, there is never too much mass near the boundary. The only way to really make a lot of mass near the boundary is you need indeed the minimum to be at the boundary, and then you need to explode very fast. But this is prevented by those conditions.
But if you have a uniform, so if f is just constant, right?
Yes.
And you in high dimension,
yeah.
Most of the volume is next to the boundary. Or the step size is smaller.
So it depends on what do you mean. It always depends on, when you say that, what do you mean by closed? So the thing is that if I have my convex body here, if I do a thin thing here of size like poly 1 over n, then this has exponentially small mass. The thing is, there is mass, it's in between. Like there is no mass here, and all the mass is in between. There is no mass too close to the boundary and no mass too close to the center. It's really in this thin shell. What makes you? Yes. So that's the picture, I think, at least to me. Okay. So let's see how to analyze this in the case of the alpha strongly convex case, and you will see it's simple and nice. Okay, so the first thing that I want to do is tell you about the continuous process which is underlying this thing. So let's introduce a Brownian motion, Wt. So this is a Brownian motion. So you remember Wt plus s minus Wt. This is a Gaussian with variance s. Okay, and these guys are independent of each other, independent increment, and W0 is 0. Okay, so this is a definition of a Brownian motion. Now the point is that this type of things, you can write it using the Brownian motion. So again, now we are in the case where k is equal to Rn. Okay, there is no projection. So in this case, this equation, I can rewrite it as follows. So x tilde k plus 1. So let's use x bar. So x bar t is going to be equal to x t over eta. Okay, or rather, let's say x bar k eta is x tilde k. Okay, for k in n. And now, what I want to say is that what is the increment of x bar t in time dt? Okay, so I have two things. So I move by this much. Okay, so from x tilde k plus 1 to x tilde k, how much time does pass? So this, I think of this as time. This is t now. So eta time step pass. Okay, that's the time. So in eta, I move by eta. So in dt, I move by dt. Okay, so what I get is this is minus 1/2 the gradient of f at the previous integer point, which is x bar eta t over eta dt. So that's this part. And now I get the increment by the Brownian motion, which is just plus dwt. Okay? So this equation really gives me this process. Okay, if I look at it at integer point, from one integer point to the next one, by how much do I increase? Well, I get, in eta time step, I get eta times this gradient at the previous point, and I get this dwt during eta time step, which is exactly a Gaussian with variance eta, okay? Which is exactly what I want. But you see, as soon as you see this, what do you want to write? What you want to write is dxt is minus 1/2 grad f at xt dt plus dwt. Okay, I don't want to do this discretization. I want to really do that continuously I take the gradient and I move continuously in the direction of the gradient. I don't want to update this at discrete times. Okay, so this is the diffusion process. This is a diffusion process. And its stationary measure is mu. Okay, stationary measure is mu. Okay, how do you see that? You know, I mean, at least for me, when I look at it, it's not clear at all that this would have mu as its stationary measure. But the thing is, I will leave this as an exercise, but it's an easy one. You can write the Fokker-Planck equation. What does it mean? The Fokker-Planck equation just means the time evolution of the density of x. Okay, x is a random variable, it keeps changing, and its density, let's call it rho t, keeps changing. Okay, so let's say rho t is the density of xt. Then what you can write is that the derivative of the density with respect to time is equal, so this is a calculation, to 1/2 the divergence, so the grad dot, let's not worry about that, we don't care too much about it, of rho times grad f minus grad rho. And this is a plus. Okay, so this, and let's put a t. So the derivative with respect to time, how does the density evolve? It evolves according to this formula. So now let's look at this formula for a minute. If I plug in rho t equals mu, let's see what happens. So what is the gradient of mu? So the gradient of mu, you know, what is mu? Mu is exponential minus f. Okay, so what I get is exactly minus the gradient of f times exponential minus f over z. Okay, so I get minus rho grad f, minus mu grad f. So you see that mu verifies that this term is 0. Okay, the gradient of mu is exactly minus mu grad f. So those two things cancel, and we see that if you start at mu, you stay at mu. Okay, the density doesn't change. All right. So there are many ways to derive this. The simplest, the one I prefer, is just Ito calculus and integration by parts. The fancy way is you write what is the generator of this equation. Okay, so this has a certain generator, and this is the adjoint of the generator. That's how you move from describing the Markov chain through its generator and describing the Fokker-Planck equation, okay, through the adjoint. But anyway, this is all very standard and easy. So now we know that mu is the stationary measure. But we want to know how fast rho t goes to mu. And this is also very standard. In this case, when you have strong convexity. So when you have strong convexity, the keyword is the Bakry-Emery curvature condition, which just says the following. So well known, let's say, is the following. If I look at the total variation distance between xt and mu, Okay, so again, right now I'm only talking about the continuous time process. There are two steps. First, understanding how fast the continuous time process goes to the stationary measure, and then understanding the discrepancy between the discrete time process and the continuous time one. Okay, so this, it's easy to see that this is less than exponential minus alpha t times the chi-squared distance between x0 and mu. Okay, so what is the chi-squared distance between two, let's say, density g and h? This is just the integral, sorry, with respect to, of g, g over h minus 1 squared. Okay, you remember the relative entropy between g and h is just the integral of g log g over h. Okay, so for the chi-squared, I just replace log x by x minus 1 squared. Okay, so you get this. So why do you get this? So this is just so what? Okay, so here is how you do it. So there is this theory of Bakry-Emery curvature, which is a certain condition on the generator. So you verify that the generator verifies this. And then you get a Poincare inequality, and the Poincare inequality directly tells you that you get exponential convergence in L2. And then you want TV. So what you do is you do a Cauchy-Schwarz, and what comes out is L2 on one side and the chi-squared on the other side. Okay, so this is all standard. And now the point is that this is of order exponential n for x0 from a Gaussian. Eta something. Okay, so you have a starting point which is from the Gaussian. So the contribution of the starting point is exponential n, and then you decrease exponentially fast. So what you need is at time t, which is of order. So what is it? It's n over alpha log 1 over epsilon. You're mixed. Okay, you're at distance epsilon. For the continuous time process. Now, how do you compare the discrete time and the continuous time? There is an exact equality, not for the total variation, but for the relative entropy between the two. This is called Girsanov, and it's very simple. It goes like this. So the TV between x bar t and xt, it's less than 1/2, so square root 1/2 the relative entropy of x bar t with respect to xt, which is equal. Okay, this is an equality, so it can only be so deep, and it gives you this 1/8 of the integral between 0 and t of the integral of what? The expectation of the norm of the gradient of f at xt minus the gradient of f at x eta t over eta squared dt. And you get the square root. Okay, so this is an equality. And this is Girsanov, which is just the fact that our two processes are two Brownian motion with different drifts. So they are absolutely continuous with respect to each other, and you can write down exactly what is you can make sense of what is dx bar t over dxt. Okay, which is what you need for this type of integral. And you get this formula. Okay, hopefully I will have time to tell you what we did, because all of this is well known. But it's important background. So now the thing is, now we use beta smoothness. Okay, so this is less than beta squared times the expectation of the norm of xt minus x eta t over eta squared. Okay, and this is all x. There is no bar. Okay, it's a continuous time thing. But now how far are those two guys? So there is the part that comes from the drift. So the drift during time step eta, it drifts by eta. So you get an eta squared. And now what about the Brownian motion part? Well, the Brownian motion part during eta time step, it has a variance eta. Okay? But it has a variance eta in every dimension, and you have n dimensions, which are summed for the Euclidean norm squared. So this is upper bounded by, let's say, 2 eta n. Okay. so now you see how small you should take eta, right? Because what you get is, in the end, that this is upper bounded by square root of, let's see, so we get beta squared over 4 eta n t. Okay? So now, what is t? T, we said, we take it to be n over alpha. Okay, so let's forget about alpha, beta, and the constant, and let's just focus on eta and n. So t is like n, so we get square root eta n squared. Okay, so what you want, so you want to take eta to be epsilon squared over n squared. Okay, if you take eta to be epsilon squared over n squared, you get that this TV is less than epsilon. Yes? Yes?
This little t there. So it says TV of x bar little t.
Yes.
And xt. What is this little t? This is for?
Yes. For any fixed little t, this is true. Okay.
What's the relation between little t and big T?
So I'm going to apply this at big T. Oh, yeah, I see what you mean. Okay, good. Thanks, Ofer. This is, okay.
So they drift away. I mean, as time goes by, they get farther away.
No, the point is exactly because of Girsanov, you don't do, you don't add, like they don't escape from each other. Like they will stay close. Those two things, that's what I was saying, they are absolutely continuous with respect to each other. So the Brownian motion part brings them closer again. And it makes sense, I mean, this is just a, yeah. I mean, there is some magic here. I mean, they are drifting away because you see this t, when t gets large, okay. So that's why you need, as t becomes bigger, you need a smaller eta. If you want to be good at a very large time, you need a small eta. But still, this is pretty sharp. I guess that's what I was saying. But you're right. At a fixed eta, if you look at 2 large times, then they will drift away. So now you just, okay, I didn't say it, but of course you apply just the triangle inequality. Okay, good. You tune those things and you get that what you need is, so k, so what is n? So what you want is n eta to be t, okay, which means that n is like n cubed. Okay, so this needs n cubed, and that's what Dalalian proved. So now what is the issue for us with the projection?
What was capital N?
Capital N is a number of, so you have the parametrization in terms of time, continuous time, and the one in terms of discrete time step. So capital N corresponds to capital T. Sorry, this is not a necessary notation. So now, okay, now what are the issues for us? Okay, everything breaks. Nothing works. First of all, it's not clear at all what is the diffusion process to write. Girsanov is not going to apply because, when the things get, the two processes are not going to be absolutely continuous with respect to each other. So we need something completely different. Thankfully, mathematicians did all the work for us. So we don't have much to do except put the things together. So there is this problem called the scorecard problem, which goes like this. So you are given W, which is, let's say, from 0t to Rn, piecewise continuous. Okay, it's a piecewise continuous function. And here is the question. Does there exist x and phi, okay, from 0t to Rn, such that, one, you want that x of t is always in k, in your convex body. Okay, so the thing is, I'm going to define for you what it means, a reflected version of a continuous path, or piecewise continuous. So you want that x stays in k. You want that x of t can be written as w of t plus phi of t. Okay, so far I'm not doing much, okay? But the last one is a critical one. The last one is that phi of t basically only increases when x is on the boundary. Okay, so phi of t can be written as minus the integral between 0 and t of nu s LDS, where nu s is the outer normal at xs. Okay, so if I have k, right, what is the outer normal? It's this thing. Okay, that's nu s if xs is here. And L is a measure supported on the set of times such that x of t is in the boundary of k. Okay, so this thing only increases when I'm on the boundary. Okay, I'm just pushing xt. I'm just allowed to push w when xt comes on the boundary.
Without the orthonormal thing, it would be again trivial because you could just wait until you get to the boundary and then stick there.
Without the yes, absolutely. So the theorem from Tanaka, 79, is yes. Okay, so does there exist x and phi such that yes, and if w is continuous, so is x and phi.
So can you just describe what's the
yes
of this like? What was the original motivation of this problem, or like, is there any?
The motivation is very clear. Look at the picture.
What is this?
Yeah. So you have k. Okay, you have a set of constraints, and you have some path. I don't know, like this in Rn. Okay, this is a function in Rn. This is a path. Okay, does that make sense?
Okay.
And now what I want is to make sense of what it means to reflect w so that it stays in k, but it mimics as much as possible w. Okay. So this is what I'm going to draw now is x. So x goes like this, it follows, and now it says, oh shit, he's asking me to go out. So it just sticks, and whenever, okay, maybe this was not perfect, but whenever, it gives me the opportunity, I follow it again.
Using the phi, I see.
You see, here I follow it again. And now, it can be, I can basically mimic it, and then here I'm going to stick, and then, okay.
Reflection seems an odd word to use then.
So the thing is, this is definitely not a Brownian motion path. So for a Brownian motion, it will really look like a reflection, but not in general.
Well, it would look like a reflected Brownian motion, but it wouldn't look like a reflection of the original one. I mean, reflection usually implies that they actually reflect. You reverse, you apply a transformation.
Yeah. So again, for what? But for Brownian motion, it's true that it's equivalent.
It's true that it's a reflected Brownian motion, but it's not a reflection of the original path.
Yes, that is true. Yes. That is true, but in distribution it is equal. But otherwise, you're totally right. Okay, so that's what we're going to use. What's the construction? The construction is very simple. Construction is doing projection. So if let's not do the construction. But the thing is, Tanaka also proved a certain continuity. So, or rather a certain Lipschitzness of this process. The map from W to X is Lipschitz. So if W and W bar are two paths which are close by, then the reflected version will be close by. So let's see, let me tell you. Okay, so now let's focus on F equals 0. Okay, so now I just want to sample from the uniform measure on my thing. So what I claim is that x tilde t, or x bar t, is the Tanaka path of a Brownian motion at discrete times of w t, of w eta t over eta. Okay. So what I do is that I have this Brownian motion that I only look at this multiple of eta times. And when I look at it, what I want is to project. Okay, so when it stays inside, I stay inside. But when it goes outside, I project it back. So it's exactly what my process is doing. When it can do the Gaussian jumps, it does it. And if the Gaussian jump takes me outside, then I project back. So x bar t is exactly the Tanaka path of wt. And what is the natural equivalent is xt, the continuous one, is xt Tanaka path of wt. Right? It makes a lot of sense. By the way, just so you see this viewed in a differential equation, this, I can also rewrite it. What is this? This means that dxt is equal to dwt minus eta t LDT. Okay, so the key difference with respect to before is this term. Okay, the term with the local time L. Okay, so now we understand that our algorithm, our discrete time algorithm, is the Tanaka path of a discretized Brownian motion. And what we want to do, we want to do two things. We want to analyze the mixing time of this guy with respect to the uniform measure, which is not so easy. And we want to understand the discrepancy between the two. So the discrepancy, let me tell you both quickly.
So, sir,
Yes?
just as a high-level question, so
Yes.
could you have tried to just, rather than go to the projection in the first place, could you have tried to put a self-concordant barrier there and just do the whole thing unconstrained instead?
Yes, but this is not so easy. We are thinking about it, and other people are thinking about it. And
Okay.
probably this will go much beyond what I present. So the hope is to get mixing time of n, or even square root of n, or even dimension 3 for the case of gradients. But this goes way beyond what I'm presenting. Okay, good. So let me just tell you. So Tanaka proved actually the following thing. If you have w and w bar, then x of t minus x bar of t squared is less than w of t minus w bar of t. Okay, so again, I have two paths, w and w bar. I'm solving the square code problem. I get x and x bar, and phi bar. And I get plus the integral between 0 and t of the inner product between w of t minus w bar of t minus w of s minus w bar of s, and inner product between phi of ds minus phi bar of ds. Okay, so this is Tanaka's result. So it's giving me some notion of smoothness of the map from w to x. So this, it's easy to see that it implies that the expectation of x t minus x bar t is something small. Okay, I'm going to be slightly less precise now because I have 5 minutes. So this is a bound in Wasserstein distance. Okay, this is a w bound, w1 bound on xt to xt bar, x bar t. Okay, so the Wasserstein distance between two measures, nu and mu, it's the infimum, let's say in LP, it's the infimum over x and y, which is a coupling of mu and nu, of nu and mu. Okay, so x as the distribution of nu and y as the distribution of mu of the expected LP distance between x and y. Okay, so this is exactly a W1 bound. But what I cared about is the total variation bound. Okay, and of course this, I mean, just intuitively, it's not true in general, but intuitively, this is much smaller than the total variation distance because it scales with the distances. Okay, so if the distances are small, this will be small, but the TV could still be very large. Okay, so there is an issue of how do you go from W1 to TV. And I will give you that in a minute. So from W1 to TV, how do you do it? It's not clear in general, and we'll do it now. But before that, what about the mixing? So the mixing of x bar t, of xt. So the mixing of xt is actually very simple. It's, I think, something very well known. So what you want, okay, you want the TV between xt and sorry, I'm. So what? Oh yeah. Okay. So to evaluate the mixing, what you need is to evaluate how much time it takes to couple from two different starting points. So if I start at x and x prime, I want to know for the worst x and x prime how much time it's going to take before the two meet. Okay, so I get two paths, xt and let's say x prime t, and I want to know how much time it takes before the two can be coupled. So what I want is the TV between xt and x prime t. And this is actually a one-dimensional problem. Because you see, what I can do is I can couple the two Brownian motion so that whenever these guys want to go to the right, this guy goes to the left, and vice versa. Okay? And this is really just about the distance between the two. So what I can put is that I look at those 2 points. Okay? I look at the hyperplane that separates those two things. And what I do is a reflection, a mirror, okay, with respect to this hyperplane. Okay, so when this guy goes like this guy goes like that. So now I just have a one-dimensional Brownian motion for the distance between the two. And the question that you need to ask is, I have a Brownian motion that starts at the distance between x minus x prime. Okay, what's the probability that it doesn't hit 0 before time t? This is exactly the question that I need to ask what is the probability that those two did not meet before time t. Because once they meet, I can just keep them together forever. And this is a simple bound. This gives you x minus x prime over square root 2 pi t. Okay? So you just need, if this is a constant, then you just need constant time. And we know from general principles that Yuval told me that after that, once it has mixed to 1/4, then it's exponential after that. So here you get a log 1 over epsilon. Okay, so this is for the mixing time. So now we know that it mixes fast, and we have this argument. So let's go back to from W1 to TV, which is the last part, and which is coming back to the question you asked at the beginning of her. So the key point is the following. So here is a simple lemma. It's really 3 lines. So the measure of the set of points which are at distance from the boundary at least epsilon. Okay, so the measure of the point, this is at least 1 minus n times epsilon. Okay, and with an r, where r is the radius. Okay, so again, I'm in the uniform measure case. In the general case with a general potential, you can do this. It's also very easy. So most of the mass, if you at scale, 1 over n or 1 over n squared, most of the mass is away in distance from the boundary. Okay, this is just a trivial bound. So now here is what we do. So now we know that the two processes, xt and x bar t, are closed in W1. And we want to say that they are closed in TV, meaning we want to really couple them so that they actually meet. Okay? Because, let me just say one. Okay, no, let's not say that. So now we know, so let's say this distance is epsilon. And we know that we have xt and x bar t. And those guys are closed in W1. Okay, so we know we can wait until this distance is, let's say, epsilon prime, which is much smaller than epsilon. Okay, so those two are closed. And we know we are at a time which we are also at a large time where xt has already mixed. So xt is like from the uniform measure. So we know it has to be away from the boundary. So this picture is really the correct picture. Xt is away from the boundary at distance at least epsilon. And x bar t is close to it. But now observe that unless there is a projection, xt and x bar t, they follow the exact same process. It's only when there is a projection that the processes are different. So what we can do is we can apply the previous argument. As long as they meet before they touch the boundary, we're done. And we know exactly how much time it takes for them to meet. Okay, this is this argument. And we know how much time it takes for them to hit the boundary because it's a distance at least epsilon. So we can show, you set epsilon and epsilon prime so that they meet before they touch the boundary. And now we have a bound in TV instead of having a bound in W1. And now how do you generalize what is currently on the board to the case where f is not equal to 0? It's just Girsanov everywhere. And that's it. OK, thank you.
So just kind of on the how, like where does your giant polynomial come from in this analysis? Like how you just kind of pick it up on the way?
Well, you see here I'm saying epsilon prime has to be much smaller than epsilon. So here every time you lose things in terms of n.
Oh, I see. So the gaps that you require are always
yes,
of n.
Yes,
So
you lose, exactly. You lose, I mean, in this part of the argument, you actually lose quite a bit. And there should be a nicer way to do it, but we don't know how to do it. And just a comment, so we did experiments, and these are currently only small scale because those things do not work in really high dimension, so it's dimension up to 100. And we're trying to estimate the volume of some convex bodies. So Vampala and the students, they have an implementation where they use hit and run. So I went into the code and I replaced every line of hit and run by just a stochastic gradient descent. And what you get is something that has the same accuracy and that is faster in most cases, but it's not by an order of magnitude. Okay, it's just a little bit faster. Now the thing is, we plugged stochastic gradient descent in the middle of this big loop that they have to compute volumes. What I really would like is to estimate how much better is stochastic gradient descent with respect to hit and run to mix. But how do you evaluate if you have mixed or not? It's not such an easy problem either. That being said, things can be done, and I think it's an interesting problem to work on this.
What can be done?
Well, you can, well, one thing you could do is you could try to estimate online the spectral gap. And if you have already mixed, then you should have a good estimate of this. But
the argument doesn't go the other way.
Yes, that is. Okay, so definitely what you could do is you could have a battery of statistics that you want to test. Whether they cover everything that you want, of course, it's not clear at all, but maybe you can make some assumption. Maybe under some assumption on the Markov chain, there is a set of statistics that you can test to check if you have mixed or not.
This is a big problem. We don't know.
Yeah, of course. I'm not saying. Yeah, of course, it's a big problem.
Can you at least try on special cases where you can actually maybe sample? So if you could sample from the uniform distribution, then you could try to evaluate, right?
you could just run like a test, just a standard test, right?
Yes. But yeah, what kind of tests do you do?
Oh no, I'm just whether are they like two sample tests, like
Yeah.
like so if you have an exact sampling algorithm,
good point. Absolutely. Yes, that's a good point.
To sample
you
tests.
can definitely do that. Yes, and indeed you can run. Those things even if you run it for a hypercube, they are doing non-trivial things. So and sampling from a hypercube is pretty easy. So.
You could also try to just run a 2-sample test between hit and run and this actually.
That's another.
That's a good point also. Yes. No, you can do many things. I agree.
Also, you described Rn and this was bounded. So like this assumes K is bounded, right?
Yes. Yes, it assumes that K is bounded. So you can always, because it's log-concave. It has light tail. So after some point there is no more mass. So you can always cut it in the analysis to this. You see what I mean? So at which level are you asking the question? For the algorithm or for the
No, you're saying this is without loss of similarity. If you're saying f is not constant, then you can assume it's bounded.
It's always the case that far enough, there won't be what?
From the minimizer?
Yes, from the minimizer, there won't be much mass left because it's log-concave. So that's always true. Now the bound that you get on how far away is far away is going to be again polynomial in n, and so it will again enter. You will get some discrepancy. So you're asking if we could apply this analysis to the case where k is unbounded. That's the question?
No. My question was.
But, yeah.
No, that doesn't matter.
Okay. Sebastian.
Thanks.